Let us now talk about the most important notions related to memory system. When we ask ourselves the question of what does a processor do, the processor does not compute stuff. The only thing the processor does is to manipulate data. And it does manipulate data that is located where? Located in memories. So a processor only sees memory. Processors only deal with memory, and therefore the memory subsystem of an architecture has to be very tightly linked to the core in order to get good performance. How does a processor access to this memory? That's what I said. It does do that through the memory subsystem that is a data bus with access and data. In the ARM architecture, the ARM Cortex-M0 architecture, we have 4 GB of memory address space. And this space is architecturally defined into a number of regions. The goal of those regions having a recommended usage, and it's here to help good design practices so that you can easily port a piece of code from a device to another. Here is the ARM Cortex-M0 memory map. So you can see the entire 4 GB memory space, and it's organized into chunks of 0.5 GB and 1 GB. At the bottom of the memory space, you will find the code space. This code space is used to store program code, as well as the exception vector table we'll cover in details when we'll talk about interrupts. Immediately followed by the SRAM location that is made to store any data memory. And finally, you will have your peripheral memory space. Your peripherals being memory mapped into the bus, the address space of your processor in order to enable easy access. In addition to that, you find this chunk of 2 GB of data reserved for external RAM and external devices. Think about it as if your microprocessor gives you access to the data bus, you can put a lot more outside of your chip. Those parts being more related to what you will find inside of your chip. Finally, at the top of the memory hierarchy, you'll find the system memory space that is used for private peripherals. Private peripherals, in a sense, private to the core. So the core will include debuggers, interrupt managers, and so on and so forth. You might want to control them, but they will be essentially linked to the ARM core itself. So of course, this is just a regular generic memory map, but every vendor will have a different specific memory design. So indeed, although all Cortex-M0 have a fixed memory map, the usage of memory is actually very flexible. And as I discussed initially, many different vendors use ARM processors. They have different peripherals, they have different memory systems, and therefore they will be able to map their different peripherals and memories to the right location inside of the memory map. So for instance, in embedded systems, you do have different types of memory. You have flash memory that will provide you non-volatile storage of your program code. You have SRAMs that will provide quick, versatile scratch memory for your data. You have ROMs, where you will be able to find all the low-level firmware that is used at, for example, to load your personal firmware in the flash memory. You need a little bit of bootloader right there. That's what the ROM will do. And inside of this memory, there are different manipulation strategies. You can have regular access, you read from an address. You can use a memory stack. We'll discuss that in detail as well. You can use a heap for instance, when you use dynamic memory allocation. So the real question with all this flexibility is, how does a memory map of a real system look like? And I'm going to show you what we have in our STM32 F0 processor. So this is just an overview of our memory subsystem for our microcontroller. The core, being right there at the top left, communicates with a large set of different memories. The flash memory, the SRAM, and so on and so forth. So how does that look like? Here is our actual memory map. So as you can see is that inside of the code memory space, we do actually have our flash memory located at the bottom of the memory space, And at the top of this region, you will find some system memory option bytes. Option bytes being used to lock your memory, to do all sorts of special operations. As part of this is directly followed by your SRAM, and as you can see, we have a very limited amount of space because we're limited to only a couple of kilobytes of every single memory system, definitely not 0.5 gigabytes. The same goes for your peripheral, where the peripheral address space is divided into several regions for the APB and AHB buses. We're going to talk a little bit more about that right now. So, good. So a few words about the AHB and APB buses. So your Cortex M0 core has a 32-bit system interface that uses the AHB Lite protocol. So AHB stands for Advanced High Performance Bus, and it's a protocol defined in the AHBA standard that has been developed by ARM and is currently an industry standard. So basically, the AHB bus is designed to support read and write transfers with different data widths, with pipeline operations, support for wait states, slave responses, and so forth and so on. So the bottom line is that it's a very high performance communication bus, parallel communication bus that is designed to enable maximum flexibility and performance in a complex system. For slower devices, a secondary bus segment is often based on the APB bus, standing for Advanced Peripheral Bus, and that tolerates, again, different set of performance, and that is very well suited for peripherals. And the two buses are connected using a bridge that will make a communication between your AHB buses into your APB bus, dealing again with bandwidth differences and speed differences. So if you now try to remember the slide I showed you about the generalities about microcontrollers, you can now see that the memory subsystem is usually handled with the high-performance AHB bus, while the peripherals are connected with an APB bus. Talking about peripherals, the most important question to ask is, how does a peripheral work? So a peripheral is a module that does something specific for you. But how do you access it? How do you control it? Usually, you will connect this piece of hardware to your peripheral bus, and it will simply be used as a device interface on your bus. So when you do that, you will actually simply read and write data into memory spaces, and this memory space being used as control registers, buffers, input-output buffers, queues, and so on and so forth. So what components do you need to actually interface a peripheral with a bus? The first thing is that you need a bus interface, you need controls, and you need registers. Your registers being your local memory space you will keep reading and writing. So that way, a peripheral is simply accessed and controlled as a memory, which makes the programming of this peripheral very easy. You simply have to look at the documentation, try to see which bits in the memory should be set to which value to control a given function, and then you will simply have to write into this address location some set of informations. So in the end, controlling a peripheral is simply read and writing memory locations. And this is what we call the memory mapped peripheral. Now, as a side note, I told you at the beginning that a processor only sees memory. This is even more true. Not only you do see the memory from your memory subsystem, but you also see all your peripherals as memory elements. So the only thing that you do with your processor is read and writing into memory locations. To give you a more general overview, here's typically what an input-output bank will look like. You do have some external pins, so that's the outside of your chip, and these pins are usually controlled with flip-flops, registers that will be used to either write a value outside of your chip or latch a value inside of your chip. So if you look into that very simplistic representation, inside of your processor, the only thing that you have are memories that you can write into or memories that you can read into. And this is what you will have with now your bus interface. Your bus interface will simply put addresses and data bus in order to control those different memory elements. Things are obviously a little bit more complicated than that. This is coming from the technical documentation of our processor. And as you can see, we still find the general concept I just mentioned. We do have our input data register and output data register that are directly interfaced with our bus from the processor. But you will also find quite a bunch of additional circuitry in order to create pull-up or pull-down network, in order to deal with push-pull or open drain, or disable the output of your I/O pin. You'll also be able to implement such bit triggers on the input, or to connect your pin to specific peripherals. While things do look a little bit more complicated, controlling those different functions will very simply done by simply writing some control codes into specific memory locations. These memory locations being called control registers, and that will be most of the focus on our labs this semester in order to understand how to control various peripherals using these techniques of a memory mapped control register.